Okay, welcome to lecture 3 of the transducers. Uh, we recollect, let us recollect what we learned in the uh, top last two lectures. Uh, we learned about characteristics of transducers, resolution, um, full scale, uh, sensitivity, the proof range or overload factor, then the accuracy of the transducer. A transducer output can have two types of errors. That's what we learned. One is called systematic error. The other is the random error. The systematic again has loading error and instrument error, right? The random error, of course, is just one, normally because of an external natural interference or man-made interference like noise. And uh, the systematic error is given in terms of accuracy. So I say I have a measurement of 100 Pascal. Let's say 100 Pascal is too small. 100 kilopascal, the error could be plus or minus 1% or 1 kilopascal, right? So this is the error. The systematic error has its characteristics that it can be computed and corrected. We'll talk about this later when we talk about calibration of transducers, how we can calculate the error, compute the error, and even compensate the error if I have systematic error. On the other hand, when random error occurs, there is absolutely no way we can do this. And when random error occurs, we take multiple measurements, right? And take the average value as the best value. Uh, let's say theta 1 comma theta 2 dot 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 theta n 1 by n sigma j equal to 1 to theta j 1 to n theta j. So then we calculate the deviation, particular deviation theta dj is theta j minus theta bar, and we have already seen that sigma dj equal to 0 and sigma dj square is minimum. If I add all the deviations, it will go to 0. That is how we calculate the uh, average value. And when you have large number of measurements, we saw that we can plot the actual measured value, right? Let's say this is theta, and the number of times that particular value has occurred. It can happen number of times. Many times it's not possible to take each value and plot. So what we do is we take intervals. Let's say 90 to 90.1, 90.1 to 90.2, 90.2 to 90.3. So several intervals, and then within the interval we calculate the number and plot them like this, right? So let's say I make 1000 measurements and maybe 400 sorry 400 will be too much. This I would say 260, this is 250, this is 200, 210 and so on. This is maybe 50, 10. whatever it is, the total must be 1000, that we know, right? And this kind of plotting is simply called histogram, right? And we also saw that if I divide, instead of put number of measurement times the measurements, if I particular nj measurement has gone, I express as a total, then I will get something like this. So all value will be less than 1, so they will become fraction. And if I add all the values, sigma nj by n, uh, j equal to 1 to n will be equal to 1. So if I now start reducing it, we may get this is the value. Now we will say probability of getting that value, right? Because we already learned that if I get 200 readings within the range 90.1 and 90.2 in 1000 readings, then I can say the probability of obtaining the range reading in the range 90.1 to 90.2 is 200 by 1000, which is 0.2, right? So we can now put a curve like this, right? And the thing is, this gives all fractions, and the area under the curve must be equal to 1, right? So we call this as the probability uh, of obtaining the measurements in a particular value. And we also saw that if we want to represent this, we can use the Gaussian equation, right? Uh, where we have y is equal to v 1 by sigma into root 2 pi into me e power minus half into x minus x bar by sigma whole square, where sigma stands for the standard deviation, x bar is the average value of the measured, uh, the number of measurements that we have taken, right? So the uh, we also learned that when we get random errors, we indicate the result as the average value theta bar plus or minus the deviation, right? D can be D max, which is compulsory if you have manufactured things that need to be fitted. Last class we saw that the bearing and the rod in a fan, you have to have maximum deviation specified. Your RMS or standard deviation will not work there. And when we say Dmax, there are two possibilities: unipolar Dmax or bipolar Dmax. Unipolar is 0 and minus x plus 0 minus x, or plus x minus 0. Bipolar, of course, I can have plus or minus x, or plus x1 minus x2 is also possible, right? That's very rarely used. If it is d is deviation, either we can use sigma RMS or sigma standard. Right? The only difference between this, as I already said, is in one case we use all the deviations, in the other case we use only n minus 1 deviation, mainly because if I have n deviations, there are only n minus 1 independent deviations. Okay, so the standard deviation sometimes is also called precision index. And the random error is also tells us what is the precision in my measurement. Now the problem is you have two errors. One error is accuracy, the other error is precision. So how can we distinguish between these two? One way to look at is accuracy tells me how close I am to the true value, right? So the easy way to understand, if you look at any standard book, uh, is to find an analogy of a dart board game. I don't know how many of you are familiar with dart board. You have concentric circles with different colors and patches, right? This is not just circles, there will be patches here, right? And we call this as bullseye. And you stand at a distance from the board, you throw arrows, right? And if he hits a bullseye, you get the point, 50 points or 100 points. Of course, if you hit somewhere here, you get only 5 points, right? So it shows you how is your aim in throwing arrows. Now if I look at this uh, dartboard, and let me say uh, let me simply say that I have 4 arrows continuously thrown. So I have all the 4 here, right? Exactly on the bullseye. Then this is this arrow thrower has accuracy because he's very close, always on the bullseye, as well as accuracy, okay, precision, because he is repeatable. He is possible. Let's say there is another uh, player, player B. I am marking it in red. Throws like this. Of course, he is precise, more precise, because all his throws are at the same place. Repeatability is there, but he is not accurate because he is away from the bullseye. Now we can have a third person who throws like this. So this person is neither accurate nor precise, right? So precision tells us how repeatable the measurement was, and accuracy tells us how close was the measurement to the true value, right? When we talk about precision, we really sometimes is also known as confidence in measurements. Uh, so if I have 2%, my precision index is 2%, then I am confident that 98% of my measurements are correct, right? That's one way of staying the precision index, right? the uh, the way that we look at these two errors are completely different. The same way we started learning about propagation of errors. So we started systematic errors, right? So we found that if I have y equal to x1 plus x2, this has an epsilon 1% error, this is epsilon 2% error, then y epsilon y percent would be equal to x1 by y into epsilon 1% plus x2 by y into epsilon 2%, right? And we also derived the formula uh, that if I have y equal to f of x1 comma x2 dot dot xn, where each is measured value error with an error of epsilon 1 epsilon 2 up to epsilon n, then epsilon y, error in y percent, would be x1 by y dou f by dou x1 into epsilon 1 plus x2 by y into dou f by dou x2 into epsilon 2 dot 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 xn by y dou f by dou xn into epsilon n. So the way the systematic error propagates depends upon the sensitivity of the function that I use to compute the final results, right? And we saw the easy things for uh, addition and multiplication, right? And we can look at the other things. For example, if I have y equal to x1 minus x2, right, where this has epsilon 1% error and this has epsilon 2% error, right, then epsilon y, of course I can say x1 by y into dou f by dou x1. x2 is an independent value compared to x1, so if I differentiate, this will go to 0, so I'll get 1, right? So into epsilon 1% plus x2 by y. I'm using this formula, x2 by y. If I do this, I will get not plus, minus 1, so minus epsilon 2%. But please remember, the epsilon 1 or epsilon 2 are plus or minus, right? They could be either plus or minus. So this I can translate it as x1 by y in the epsilon 1 minus or plus. Earlier it was plus or minus, so this is plus or minus. Minus or plus x2 by y into epsilon 2. So here it is plus minus, it's minus or plus. But we really do not know whether epsilon 1 is going to be positive or negative, unless otherwise we actually make a calibration, right? We measure and see what is the error at that point. So both plus and minus are equally likely. So in a worst case, I can simply say x1 by y into epsilon 1 plus x2 by y into epsilon 2, right? So you have to be really very careful when you are subtracting. Even though we are subtracting, errors add up. Worst case error add up. Let's take an example here. I have let's say value of 100 plus or minus 1%, right? And I have another value plus or minus, this is x1 is equal to 100 plus or minus 1%, x2 equal to 90 plus or minus 1%, right? So now I can uh, say y, I am adding x1, I'm subtracting x1 minus x2, so that would be 100 minus 90, that is be 10. But what is the error? Epsilon y would be 100 by 10 into 1% plus 90 by 10 into 1%. So that would be, this is 10%, this is 9%, that is 19% error, right? So even though I have measured x1 and x2 with 1% accuracy, the moment I do x1 minus x2, my result worst case error could be 19% in error. So the moral of the story is, if you have to subtract two quantities, do not measure and subtract, subtract and measure, right? I can subtract x1, x2 and then measure it. Even with a 5% accuracy, that's better than 19%, right? Uh, Now, if we say that u is equal to v plus w, where u, v, w are measured values with random errors. So this has v bar and sigma v. This has w bar and sigma w, right? Then what will happen to u bar and sigma u, right? What will be the average value? Now for this thing, let's say I have V, I have measured V1, V2 up to Vm, right? M measurements. And uh, W, I have measured W1, W2, Wn. These two need not be measured at the same. This way I could have measured 50 times, this is 100 times. So I'm taking M measurements in V and N measurements in W. So of course I know U bar is equal to 1 by N, sigma j equal to 1 to M 1 by M, because I measured, right, Vj. And W bar, not U bar, this is V bar, I'm sorry. W bar would be 1 by N because I made N measurements, sigma j equal to 1 to N Wj. Now when I come to U, I can take U as Vi plus Wj, where here I varies 1 to M, J varies 1 to N. So I can say Uij. For example, I can take V1, the measurement of value V1, first measurement. I can add it with W1, I can add it with W2, I can add it with W3, W4, W5, W6 and up to Wn. Similarly, I can take V2, add it with W1, W2, W3, Wn. So I will get totally N by M values. So this will be Uij will have N multiplied by M values, right? So my U bar would be sigma 1 by Mn, because there are total Mn values, Uij Uij, where I is equal to 1 to M, J equal to 1 to N. So I can now expand this. U bar is 1 by Mn into sigma I equal to 1 to M, J equal to, I say something, write something else. I equal to 1 to M, J equal to 1 to N. Uij is nothing but Vi plus Wj, right? So that would be 1 by Mn. I take this, sigma I is equal to 1 to M, J equal to 1 to N, Vi plus, this is multiplied, sigma I equal to 1 to M, J equal to 1 to N, Wj. Now I look at this um, uh, this one. I put I equal to 1, I will get V1. I equal to 2, I will get V2, right? But when I put J equal to 1, nothing. I will get V1 plus V2 plus V3 plus Vm. When J equal to 2, again I will get V1 plus V2 plus V3 plus Vm. So if I am going to evaluate this, because J is an independent values, I am going to get N times sigma Vi. So I can rewrite this as 1 by Mn N times sigma Vi sigma Vi I equal to 1 to M. Similarly, this would be M times sigma j equal to 1 to N Wj, right? Again divided by Mn, because Mn is common for both. So I can cancel this. So this would be 1 by M sigma I equal to 1 to M Vi plus 1 by N, M cancels, N cancels, sigma j equal to 1 to N Wj, or this is uh, V bar plus W bar, right? So of course in the set theory we have an equivalent, right? uh, uh, thing that we learned, average value of a sum set is equal to sum of the average values of the individual set, right? Uh, Now let us look at sigma u. I am not going to use that -1 because that's slightly complicated. So I am going to use RMS value, right? The sigma is RMS value. So I can put this as square root of 1 by Mn sigma uh, dj square uij minus u bar whole square, right? This is I equal to 1 to M, j equal to 1 to N. So that's the RMS deviation. Even if you put standard deviation, it will come, but this is much simpler. So now I can put this as let me take the square on this side so that I can uh, sigma square, right? I can put sigma u square. I can get rid of the square root so that I don't have to write square root every time. Right? It becomes 1 by Mn sigma I equal to 1 to M, j equal to 1 to N. Uij I know is Vi plus Wj, right? That is Uij minus U bar we already calculated, minus V bar minus W bar, right? Whole square. Okay. So this we can write it as sigma U square is equal to 1 by Mn sigma I equal to 1 to N, j equal to 1 to M, j equal to 1 to N, right? Uh, this I am going to write it as Vi minus V bar whole square plus Wj minus W bar whole square, right? So actually this Vy minus V bar whole square, Wj minus W bar whole square minus plus 2 Vi minus V bar into Wj minus W bar, right? So let us expand this. This we have already seen. When it comes to V, only I stands. J simply becomes, I do it n times, right? So this becomes n by 1 by mn sigma I equal to uh, I equal to 1 to m vi minus v bar whole square, right? Similarly, if I take this one, this is again over I and j. I is an independent variable, only j is a dependent variable here. So I will get sigma j equal to 1 to n wj minus w bar whole square, and I will do this over I varies m by mn, right? Now this sigma, both I and j are there, so I'll have to put 2 by mn, right? Sigma I equal to 1 to n, j equal to 1 to n, I equal to 1 to m, j equal to 1 to n, vi minus v bar into wj minus w bar. Now if I look at this, what is vi minus v bar? That is the deviation in vi. And what I am doing, I am summing the deviation over its entire set, right? 1 to m. So this will go to 0 because sum of deviations are 0. What is this? This is deviation in wj. Again, I am summing all the wj over its entire j equal to 1. So the sum of deviations w also will be 0. So that is left. So I can cancel m here, n there, and I would get 1 by m sigma I equal to 1 to m vi minus v bar whole square plus 1 by n sigma j equal to 1 to n wj minus w bar whole square, right? Of course, this we know. What is this? This is sigma v square. This is sigma w square. So this is sigma u square. So the square of the deviation in the sum set is the sum of the squares of deviation of individual sets. This again very standard derivation in set theory. Let's not worry about it. We derived it ourselves, so we can understand this, uh, right? The quantity sigma square has a special name called variance, right? So variance of a sum set is equal to sum of variances of the individual sets, right? That's another way of putting it. Similarly, we can use longhand calculations and find out what would be the random error if I in a computed quantity, if I use measured values with random errors. This again is not a nice way of doing it. We should have a formula, right? All of you agree that formula is better to calculate things. So we once again use y is equal to f of x1 plus x1, not plus 2. It could be any function, right? So each x1 as sigma 1, x2 as sigma 2, xn as sigma 3, right? So if I want sigma y, what I have to do is first I have to put delta y. Delta y is dou f by dou x1 into delta x1 plus dou f by dou x2 into delta x2 dou xn by uh, dou f dou f by dou xn into sigma n. Sorry, we have not come to this. Delta xn, right? Uh, Now what I have to do? I have to put delta y square, right? That's the deviation square. Small deviation in y is delta y. I need delta y square summed up, right? So here I have to put delta y square. So this will be, let's say, a plus b plus c plus d whole square. I would get dou f by dou x1 square into delta x1 square, right? And uh, uh, the other way I put is dou f by dou x2 whole square into delta x2 square, dou f by dou xn whole square into delta xn square, and of course there is a summation, right? X1, each value may have any number of times, okay? X1 could be 100 times, X2 to be 200 times. We sum like that. There is no big deal. We sum y to whatever number of numbers of computations that we can do. Okay. Now the uh, one thing that we look at is that this is only a square plus b square plus c square. What about the 2ab plus 2bc plus 2cd, right? All the other products. All the other products, when I sum up, I am summing up delta x1. I am summing up delta x2. So all of them, all cross products will go to 0 because I am summing up through the entire set of measurements, and these are deviations. And what we said, sum of deviations equal to 0, right? Many times the standard deviation is expressed as a percentage. We already saw that when I say 100 ohms tolerance is plus or minus 1%, what does it mean? I have a 100 ohm resistance whose standard deviation is 1%, right? The value of the resistor manufactured would lie within 100 ohms plus or minus 1, whatever uh, that value is, right? So how do I get percentage? So percentage sigma u would be sigma y square divided by y into 100. So I now go here, I have to put a equal to, okay? Go on the right hand side. So I'll have to divide, I have divided the left hand side by y, multiply by 100. So I have to do that on all the other quantities. So I divide by y, and I have dou f by dou x1 whole square into delta x1 square into 100. 100. What we do is we do the same thing, x1 in the numerator, x1 in the denominator. Now this is uh, nothing but sigma uh, 1. Am I right? Percentage uh, sigma 1, okay, square. Okay. So we can do the same thing. So the basic thing is this is sigma u square. because we taken out the root, right? Uh, Sigma u square is equal to square root of whatever is the number of m, n, k, s, sigma, this m, this n, k, s, all those, right? J equal to 1 to m, I is equal to 1 to n, k equal to 1 to o, all those things. I have u, y, I, j, k, etc. minus y bar whole square. This is what it is. So I've taken the root, so it should be sigma u square. Please correct that. When the sigma is actually root means square, right? Square root of that. So we can now say that if I have y equal to f of x1, x2, x3, then sigma y square would be equal to x1 by y whole square into dou f by dou x1 whole square into sigma 1 square plus. So similarly, I'll write one more, x2 by y whole square dou f by dou x2 whole square into sigma 2 square. So we can write this way for any function, right? We can get the propagation of random errors too. Okay. Uh, Now we talked about the characteristics. Let's look at resolution, range, right? This is the smallest value that I can measure. This is the maximum value I can measure, right? Resolution, range, sensitivity, overload factor or proof range, right? We have accuracy, we have precision. While all these are applicable to most transducers, precision is not that encountered in real world, right? Precision comes into factor when you anticipate the measuring environment to be noisy or some external or natural uh, interference is going to affect your measurements. So this will not be very often encountered. All this would be encountered on every transducer, right? Uh, Now let's uh, do a very simple experiment, right? I have a thermometer. Assume this is a mercury thermometer, right? I have the gradations, right? And then I put it in a liquid whose temperature is theta L. Now, if you do this, I mean, in your life, you would have always measured your temperature. What we do, we put the thermometer to measure the temperature, and then we see that the mercury, if it's a mercury thermometer, mercury slowly rises and then comes to a standstill. So, if I record the height of the mercury with respect to time, the temperature will go like this, right? It takes uh, uh, something like 3 minutes, right? Or 30 seconds or 1 minute, whatever it is, right? So normally, what does the doctor do? He puts the thermometer in your mouth and he starts looking at his watch. And after some time, he takes out the thermometer and checks whether what is your body temperature. Why does he do it? Because the thermometer requires certain time to sense the actual temperature of the whatever we are measuring, whether it's a body temperature or a temperature of a liquid, and after only certain time it correctly reads. Till then it is slowly going towards the correct reading, right? So if you look at this particular actor, you can read only here. If you read somewhere here, you'll make a blunder, you'll make a mistake. So this is true for every transducer, right? Every transducer has this problem, right? So the transducer, as soon as you connect it to measure something, it takes a while, right? Some transducer can take only milliseconds or microseconds. Some may take like this, even 1 minute, 30 seconds, 2 minutes, but they will take some time, right? So if I look at on these characteristics, this period, right? This period, let me use a different color. This is known as transient period, right? Uh, in the transient period, the output of the transducer goes tries to go very close to the final value. When this is called steady state condition, right? Transient period and a steady state period. In the steady state period, of course, the measurement is steady and you can make measurements. Okay, so this is very important that when you use a transducer, that you have to wait uh, for certain times to take a reading. So these characteristics, none of this, these characteristics do not really come here. This is something different. So we call this as static characteristics. That doesn't change. Here the value changes. We call this as dynamic response, and the a transducer will definitely possess different types of static characteristics and different type of dynamic response, right? So you will have to understand this, otherwise you will wrongly use a transducer without understanding that the transducer has something called dynamic response characteristics, right? Dynamic response characteristics. Please remember here the uh, temperature is not changing. Temperature is constant, right? So this is theta L. But there is a right. We still have a problem in the transient period, and only in the steady state period we can measure. There is another type. I can have a transducer and I can give an input that is time varying, right? Then my input is dynamic. The transducer has to have certain characteristics so that the dynamic input I get exactly repeated, right? I get the same output. Okay, so the dynamic response characteristics not only talks about the transient state and the steady state for a constant input. It also tells us how the transducer output will be if I have a dynamic input, where my input itself is changing with respect to time. We will talk about dynamic response characteristics in the NAT class, so I'll stop here. Okay.